Okay, hello and welcome back, everyone. The next speaker for today is Professor Shanwen Wang from Renmin University of China, and he will speak on compatibility of explicit reciprocity laws. Professor Wang.
Thank you very much for the introduction. And I would like to thank the organizer for giving me the opportunity to speak here. So my talk is about the compatibility of explicit reciprocity laws, which is a joint work with Pierre Comets. And by official definition, since we haven't posted the article, so let me say it's a work in progress. For the convenience of the audience in this talk, I will give the details as much as possible. So my talk will be divided into two parts. For the first part, I will review what is Kato's explicit reciprocity law, and then I explain our results. Let me start with some notation. So we denote AF, the group of finite idea of Q, and A, the ring of idea of Q. And we denote by Q cyclotomy, the cyclotomy extension of Q by adding all the roots of unity. And we write a GQAB, the Galois group of Q cyclotomy over Q. And the point 4 and 5, I think I don't need in this talk. And the sixth is we write C, and the two different C knows the one is the field of p-adic complex numbers, another one is the field of complex numbers. Okay, and we have notion of modular curve. Let G be the algebraic group G2 defined over Q, and for any compact open subgroup of G2AF, we denote by YK, respectively SK and XK clause, the open and compatified with local structure at cusp modular curve or level K. And we also have the universal additive curve EK over YK. Okay. And we also use some local systems on modular curves. So there are two styles. One is the eta one and another the Han one. So for eta side, we denote by sim1 eta, the Tate module of EK, and H1 eta, the ZP dual of sim1 eta. And this Tate module has a ZP basis, denoted by E1 star E2 star, which correspond to -1 tort of the fiber at the tort of the complex identification of YKC. And on the complex side, there's a monotomic action correspond to gamma in the intersection of this level K and S2Z, which will transfer this E1 star E2 star to this element. So the formula can this action is because the monotomic action is on the right, and when I transfer to the left, we take the inverse. So that's why we have this formula. And this action induces a left action on this Tate module. And for the Han side, we have this H1 the Han on XK clause. And the section of this H1 the Han on open U is the relative the Han cohomology of the universal additive curve over U. And there's a filtration on this H1 the Han. So it's a decreasing filtration. And there's for I equal to 1, it's a line. And okay, and smaller than 0 is the full space, and bigger than 2 is 0. And this vector bundle equipped with Gauss-Manning connection. And then we can use these two basic local systems to construct more local systems. For example, we denote by WKJ. It's the sim K of H1. So eta of the Han, and tensor is this H2 tensor J. So this H2 is just the wedge of H1. Okay. And in Kato's explicit reciprocity law, so Kato's explicit reciprocity law related to special elements. One is on the eta side, another one is in the Debargha side, and so first let me introduce the element on the Debargha side. So it's we have the Eisenstein distribution. So let A be a subring of C, and we will denote by MK classic QH, which means the A module of nearly holomorphic classical modular form of weight K for arbitrary level, and whose coefficient of Q expansion are in A. So here I say the class, I put classical here. I mean all these series are in the complex analytic side. And the rational structure or A module structures comes from the Q expansion. And for any integer K bigger and greater than 1, and for alpha beta in Q over Z, there is this Eisenstein series E alpha beta K and F alpha beta K lies in this space of a nearly holomorphic modular form, and satisfies the satisfying the distribution relations which can be written in the following way. So the integration gives the distribution relation, and here D edge. So this means it's the dual of the locally constant function with compact support. So we can only integrate over the we can only integrate with locally constant function with compact support. Okay. So then we can use this two distribution to construct the Eisenstein distribution, the Eisenstein ZKato. Note that for the Eisenstein theory, almost all of them are holomorphic except in the case K equal to 2. And we can modify the preview Eisenstein distribution for this case such that all of them take values in the holomorphic space, in the space of a holomorphic modular form. And the coefficient of the Q expansions are in Q dichotomy. Okay. Then the product of modular form of weight K with modular form of weight J gives a modular form of K plus J, allows us to define this J Eisenstein Kj is equal by this formula. So in this way, we get algebraic distribution on M2AF with value in MK plus 2 classical Q dichotomy. And this element endowed with the action of J2 Z hat, which is induced by the action of J2 Z hat on Eisenstein theory. So this action is a little bit different from the formula in Comets-Boer talk, because we renormalize everything to fit things into the setting of automorphic form. So it's just a problem of normalization. You take the left action or right action. Okay. And for two elements in Z hat clause star of the form CD in, and we modified this Eisenstein distribution by the operator. So the purpose of this modification is to to make this distribution with value in how can I say, to it's to, in fact, it's to coincide with the eta side. But in this case, after we do this modification, the value, it takes value in the space of modular form tensor with QP. Okay. Then we go to the eta side, and we have the Siegel unit, which are some special modular units. So for any alpha beta in 1 over n z over z, so that means we fix the level, and we take a integer number applied to C such that C alpha C beta is not 0. Then there is this unique explicit modular unit called Siegel units, and the notation is GC alpha beta, satisfying GC alpha beta modular units for this level, and whose restriction to so here is, I should write this, to the kinetic component. This kinetic component is given by the classical theta function by this formula. Okay. And we define the G alpha beta is in the space of Q tensor O star. So here O star is equal to the direct limit of n O y n star. And this element is independent of choice of say congruent to 1 mod n. And for any C prime to 6, we can recover GC alpha beta using this G alpha beta. So by this formula. And starting from this modular unit, we can construct an algebraic distribution on M21 prime AF. So here prime means we get rid of the point 0, 0. Okay. So this is in fact this distribution, we can define this distribution because the Siegel unit satisfied this kind of distribution relation. Okay. And we have an action of J to AF on the G alpha beta by the formula. So this formula coincides with the formula on Eisenstein theory because we have this relation. So, okay. And we can extend this action of J to ZKato ZKato. And our distribution Z Siegel lives in this space. Okay. Then we can define Kato's element. So first we take the Coleman map. So here, pi q, define pi q is the automorphism of all the modular form for all the weight and all the level with coefficient of Q expansion in Q bar, and fifth, the modular form of level S2Z and with coefficient in Q. Okay, and pi Q bar prime is equal to pi Q and J to Q as a subgroup of automorphism of MQ bar. Then the Coleman map gives us element in H1 pi Q prime and with value in this space. Then we take 2 copies of this Coleman Z Siegel and we take the tensor product. Here -1 is because we want to have this kind of distribution. So I exchange the place. So if I don't take -1, then it's QQ Mkj minus cm g a over m cup. So it's another side. Okay. Then we modify this ZKato by the operator. So this modification gives the measure. So because it takes value in ZP, then this space equal to H2. So that we can integrate with continual function. And then we define the ZKato ZKato by the following relation. So this so here the pairing is for H2 close H2C to H4C2 QP2, and this isomorphic to QP. So because we are working for arithmetic, so we have this 4. So 1, and here we have 2. One is coming from the geometry side. Another one is from coming from the arithmetic. Okay, and this this pairing is you take the coupler dot and you also take the integration between the coefficient. So this gives you this pairing. And Kato construct a dual exponential map to compute the image of ZKato ZKato in the space of modular form. So his map, dual exponential map is defined as following. So let mn be 2 integers such that m plus n bigger or greater than 5, and plan the product plan to p, and we fix a place above p of this range of integer, and we take O be the p-adic completion of set as nth roots of unity, primitive 1, and F be the field of fraction field of O, and OKM is the p-adic completion of this string. So note that the Q expansion of the modular form will live in this ring. And Km is the fraction field of OKM. And we have a map from spec Km to YK. Here K is the compact open subgroup of G2 Z hat. And we have this Ym is the, so here Km is just replace m by m p to the power m, and by then Ym is the product of Ykm and spec Km over Yk. And Kato's dual exponential map is for this range. His map is map from H2 Ym Wkj eta to Oym, and combining with the this map, the open immersion from this spec Kmm to Ym. In fact, we can view Kato's dual exponential map as the Q expansion for the cohomology class in this space, in this cohomology group. Okay. And on the other side, we have the Bloch-Kato dual exponential map. So let us denote small beta Han plus and beta Han, the usual Fontaine string for C. And for this, also still for this range, we have H1F, H1 eta 1. So I have defined F before. So it's the QP fraction field of O. H1 eta YKM Q bar WKJ eta to D the Han plus. So in fact, we just extend the coefficient to be small beta Han plus and then compute the cohomology, and we get this D the Han plus, and which is isomorphic to space of modular form of K plus 2 and with level Km. And we need to tensor extend the coefficient to F. And we also have the Q expansion, which give an inclusion of this space to KMM. Then Kato's explicit reciprocity law is the following. So the first point is the diagram commutes, which means one can use Kato's dual exponential map, this one, to compute the image of this class in by the Bloch-Kato dual exponential map. And the second point is, if we applied this map to ZKato ZKato, we will get the Eisenstein ZKato. Okay. So the motivation of our study is the following 3 points. So in Coleman's Bourbaki talk, he constructed a new map to, in fact, say a variant of Kato's dual exponential map and apply to. So let me say a new one. Take the theorem ZKato ZKato, and we get exactly the same result as Kato. Okay, but he didn't prove the compatibility between this new map and Kato's map. There's no proof of the compatibility between this one or this one. Of course, he mentioned that this kind of compatibility must follow from the comparison theorem. And on the other hand, in the preprint of Francesco Lemma and I, we modify the construction of Coleman's to give explicit reciprocity law for Eisenstein class. But we have the same problem as Coleman's, so we can't get we can't explain the reason. So one of the aim of this study is to fulfill this to complete the story. Okay. The second point of this study is to understand the avatar of Urban's nearly holomorphic form. And the third one is to, because this study has application to factorization of Kato solar system, which is again joint work with Pierre Coleman's. Okay. So let me explain the results. So now we so in this talk, in the following, I will fix a level K, and the kinetic component of the modular curve are defined over Q Zn, where n equal to the number of ZK star over determinant of K. And we denote by YK analytic or SK analytic clause the analytication of YK or SK clause as adic space. And we denote by D infinity clause the open unit disk around the cusp infinity, and which is defined over the field F. So I change the field F. Before it's in Kato setting, F is the fraction field of O. Now I change it. It's just QPZN. Okay. So the nearly holomorphic modular form can be defined use geometry language. So the holomorphic one is of level K is MKK H0 SK cross omega K. More generally, if I sometimes also write KJK H0 of omega K tension H2 the Han minus J. And here the nearly holomorphic modular form of weight K and depth R is the global section of this strip. And similarly, we also have this QH KJR. I think maybe here I just put no minus. Okay, so equal to, it's just a twist. H0 and then here WKJ. Okay. And if we take R equal to K, then the nearly holomorphic form of weight K plus 2 and depth K has a decomposition. So one is the image of nearly holomorphic modular form of weight K and depth K. And another part is the holomorphic modular form. And this means if we take MK, the holomorphic modular form embed into the space of nearly holomorphic modular form and then pass to the quotient, this one is isomorphism. And on the other hand, we use this decomposition to define the holomorphic projection of nearly holomorphic modular form. It's the projection from the nearly holomorphic modular form to this space. Okay. And to study the eta of the nearly holomorphic modular form, we need to use the pro-eta cohomology. And first, we have some strip of relative Fontaine ring. So O, we denote by O the structure strip. And beta Han and beta Han plus O beta Han log. In this talk, we will omit this. And O beta Han plus the pro-eta strip on modular curve with value in the relative Fontaine ring. And the strip O beta Han plus is equated with beta Han plus linear log connection. And we have the exact sequence. And this connection coincides with the differential D on the structure strip. Okay. Now we have the Q expansion of nearly holomorphic modular form. So here I said p-adic because the base we choose will use is purely p-adic in a p-adic setting. So if Q is the natural parameter of D infinity clause, then the universality curve over this open unit disk is just GM over QZ. And the basis E1 star and E2 star of TODO module sim eta 1 specialized at this Q is E1 star is 1 ZP minus 1, and E2 is Q and Q1 over P. So record in the complex setting, this one correspond to -1 tau. Okay. Then action of the geometry fundamental group pi1 geometry of D infinity on the Tate module will factor through this gamma D infinity, which is isomorphic to ZP1. Okay. And we can choose the generator gamma of this group such that gamma S on E2 star equal to E2 star minus E1 star, and gamma E1 star equal to E1 star. And we take the dual basis of the Tate module, we denote by E1 and E2, then we can compute by the action of gamma on Tate module, we get the action of gamma on E1 and E2. It's following. Then we use the p-adic lemma here, but correspondence, we have the isomorphism. And by this isomorphism, we can construct a basis of WK Deligne using the basis of WK eta. Okay, so V1, first we do this for W1, and then WK is just the symmetric power. So V1 equal, we take V1 equal to U E2 minus T E1, and V2 equal to E2, and here U is equal to log Q theta over Q, and T is the usual 2 pi I, Fontaine's 2 pi I, p-adic 2 pi I. Okay, and then this V1 is equal to dt over T if we write T as the parameter of GM. So maybe here you can put the sign plus or minus. It depends on the choice of p-adic period pairing. And the connection of the S on U equal to du, and it gives dq over q, and which is equal to V1 square. So this identity is the translation of the Coletta-Spencer isomorphism. Okay, and gamma S on U equal to U plus T. Now we consider the restriction map. So this map is very natural because we want to study the Q expansion. So it's natural to restrict to this part, to the infinity. And because now we have the basis of WK Deligne or WK J Deligne, we can write the image of any nearly holomorphic form under the map restriction to D infinity in the following form. And so here Z Deligne is the natural basis of the motif, Deligne realization of the motif Q minus 1. Okay. So, in fact, in this talk, you can just forget about this kind of twist. Then the polynomial Q expansion of F is equal to the sum I equal to 0 to K FIQ X to the power I. Okay. So this polynomial Q expansion is introduced by Urban in his paper. And if you take F0, that means we take X equal to 0. Then it's the Q expansion of this nearly holomorphic modular form, and which is a p-adic modular form associated to F. And then we also have we have the holomorphic projection of this F, and it is as following. Okay. And here partial Q is just Q over D dq. Okay. So this is the story on the hand side. Now we go to the eta side. First, we have the following result. Compute the p-adic cohomology of the field zero of this kind of shift. So H0, this H0, so in fact, just two kind, we compute H0 and H1 and change the shift. So this H0 equal to field zero of the usual Debargha tensor with the space of nearly holomorphic modular form. Okay. And this one is similar to the second point is similar to the first point, and H1 is equal to field zero of the Debargha tensor with this H, the usual H1, the usual Debargha homology. Okay. Then we have a p-adic Eichler-Shimura map. So we just take the p-adic homology of the Z sequence 1. So let's go back to this Z sequence, this one, and we take the p-adic homology. Then we get the connecting map gives us so combining with the previous slide about the H0 results on H0, we get the p-adic Eichler-Shimura map from this field zero Debargha tensor this space quotient by the image of the connection and inject into H1 p-adic of this cohomology group. Okay. And this map has a explicit description. That means if you take any F in this space, then locally you can solve the equation nabla GU equal to F on the open apinoid U. And then if you look at the action of geometric fundamental group of UC, then you compute lambda sigma minus 1 GU equal to sigma minus 1 F, and which is 0 because F is in fixed by the action of sigma. And last, the map sigma goes to sigma minus 1 GU gives a one cocycle on this geometric fundamental group, and with value in H0, you see a Debargha tensor Wkj eta. Okay. In fact, it's in field zero, and the image of this one cocycle in the cohomology depends only on F. This is because you can choose different solution, but the different solution is of GU is just up to is different by the an element in H0 of UC Debargha this. Okay. Then we can group all these local class together to get a global class in this cohomology group. Okay. And now we study the Q expansion of this class, cohomological class in p-adic cohomology. As usual, if we want to study the Q expansion, we just restrict to the open unit disk. So we consider the Q expansion of F d infinity. So if we take F a nearly holomorphic form and in this space of weight k plus 2 depth k, as I said, we can just forget about this part. Okay. To describe this one, first we need to, in fact, to describe this class, we need to solve this equation. And the formal solution of this equation is given as following. You can just apply the lambda to G, and then you see a lot of term cancelled, and then you get F. And let partial 1 equal to log gamma. then partial 1 S on G equal to, we have this formula. And record nabla over du equal to minus q d dq. And u equal to log q theta over q. Then use using Taylor formula, and you take value at q theta. You will get this. The value of this cocycle, one cocycle on partial 1 is equal to this. So so there is a change from V1 to E1. We use this formula, and then you develop this V1 at, so okay, at the point q theta, and then you get this, and this minus power of minus 1 comes from here. Okay. Then last for any f in this space and in nearly holomorphic modular form, we denote by iota eta f is the element in of this element in. So in fact we construct before in this. And similarly for this space, so it's here, and this point is here, and this point is here. We have this we associate an element in this O theta d infinity. So O theta d infinity is equal to some I q theta I and AI in Debargha plus, and this series converge on the infinity. There is a more precise description of this ring, but here we just say this is this ring is a series of this kind of thing. And we have the is a sequence here, and no, we have the so we have this diagram, and the result is this diagram is commute. This diagram commutes. Okay. So the Gauss-Manning connection here correspond to in the p-adic in these p-adic settings correspond to partial 1. Okay. Okay. And this diagram tell us the Q expansion of so for the cohomology class here we take the restriction, and we'll go to on the hand side is this iota eta. Okay. The last thing for this cohomology class is the holomorphic projection. Note that partial 1 E1 equal to E2 and partial 1 E2 equal to 0, and partial 1 GQ theta equal to T partial Q GQ theta. Okay. And we have this the Pareto cohomology for this D infinity is isomorphic to the ring tensor Wkj eta quotient by the image of partial 1. And this is isomorphic to this module. So it has a natural base E1 to the power K. That means this Pareto cohomology of D infinity can be naturally viewed as a quotient of this space. So here is O theta D infinity. And the projection of the cohomology class to E1K gives the Q expansion of holomorphic modular form, which is, and it's just the holomorphic projection of this cohomology class. Okay, with all this, we can define a geometric dual exponential map. Oh, sorry, I defined this ring here. Okay. And so this geometric dual exponential map start from the eta cohomology of YK analytic the ID space. So maybe people don't like this K. Go to H1 pro eta cohomology of say cross AN to here, and then you extend the coefficient to beta ham plus, and then you restrict to this open unit disk. Okay, and you get field 0 of this cohomology. And this one is isomorphic by the argument we have showed before. It's isomorphic to, in fact, is you have this basis. Okay, and you just take the trivialization. Okay. And then we can define a new dual exponential map for this H2. So it's H1, and this H1 induced on the geometry level induce a dual exponential map on the arithmetic level. And when you take the Galois cohomology for this string, you will get this O d infinity over F. This means d infinity defined over F. Okay. And the compatibility of explicit reciprocity law is the following theorem. Says the following diagram commutes. So this is our new one, and this is the Bloch-Kato dual exponential map. So in fact, we start with some global class, and for Bloch-Kato dual exponential map, we only localize the arithmetic part, only localize the field, and this one we localize not only the arithmetic part, also the geometry part, and this can be explained as the Q expansion. And here you also have the Q expansion, and these two Q expansion coincide. Theorem says that. Then now I have 10 minutes to prove to explain the proof. So in fact, we only need to prove the compatibility on the geometrical side level, because the new dual exponential map and Bloch-Kato dual exponential map are both defined by H1, and so you only need to consider the geometry part. And this H1, so we start with this Galois representation, and we extend the coefficient to beta ham plus. And this is how we define the Bloch-Kato dual exponential map. And this one is isomorphic to, by comparisons, classical comparison theorem, is isomorphic to this. And if we go to the analytic side, we go to the polar eta cohomology. And we extend the coefficient to this big beta ham plus. And this cohomology is isomorphic to this one. And we restrict to, so naturally this one commutes, and then we only need to verify the lower part is commutes. And this one restrict to d infinity, and this is the Q expansion. Okay, so, and this is isomorphic to this. Okay, and now if we look at the beta ham plus, tensor this H1. So this part, so it's a sub of it. And you start from here to here, and then you retreat to D infinity. And this subspace is identical 0 if you retreat. So this map naturally factors through here. Okay, and here we have the Q expansion to this space. And this in the Bloch-Kato side, this space appear also naturally because for the later we will take H1 F, so it's naturally go to this space. Okay, and okay, so the problem leaves for any class here in this space, and this M is in fact you can write as the nearly holomorphic K plus 2 K quotient by this M. K. And that means you can take a representative of this nearly holomorphic modular form, and then you leave this to a class here. And if you have a class here, you go this way and you go this way, they coincide. You can prove this by our computation. It's big computation. In fact, this is encoded in the construction. Yeah. So this finish the proof of the compatibility. Okay. Yeah. Thank you. I think I stop here.
Thank you, Professor Wang, for this beautiful talk. Are there any questions? Yes, any question? Okay, if not, let's thank the speaker once again. Thank you, Professor Wang. And we'll resume for the next talk in approximately 37 minutes.